Hi, in this video, we are going to go into a little more details about the Grover circuit. Uh, so let's draw the Grover circuit as we have studied. So we have the top qubits. We have an application of the Hadamard gates. Then this is on the bottom register is an auxiliary register. And then we have several applications of what is called as the Grover operator, G. And then finally, we have a measurement at the end, and we get our answer of the marked elements. Right? We have gone into a little bit about the Grover's operator. So the Grover's operator, as you know, is a combination of two things. So G is U of F followed by R psi. Right? So, and if you look at the picture, we have the two-dimensional picture that we have is the following. So our input to the Grover circuit uh, over here, and this point is this vector psi, which is the uniform superposition vector. So this is equal to summation 1 over square root of n, summation over x. And then we have the two-dimensional subspace spanned by these two vectors, where this vector is the solution space. And this is another superposition of vectors that are not in the solution space. And we have this theta over 2. So this Grover operator, it's a combination of two operators. The U of F operator reflects about psi of S per. So initially, the U of F operator reflects at about this vector and goes, and then the R of psi operator, which is this operator, this reflects about psi. So then effectively we have two reflections which combine to form a rotation. And the angle of rotation is theta, and theta is equal to 2 sine inverse of square root of m over n. Right? So in this video, we want to sort of figure out how to construct the U of F and R of psi operator, right? So let's get into that. So how do I construct? So you want a vector operator U of F when it's acts on X, then this is minus 1 to the F of X. So you want a sort of gate implementation of this operator, and F of X is equal to 1 if X is marked and 0 else, right? So how do you implement U of F? Well, we can do it using the Toffoli gate. So Toffoli gates, and Well, if we have a multi-qubit Toffoli gate, then we can do this implementation. For example, let's say we have n is equal to 2 to the power 3 is equal to 8, and let's say 101 is a marked element. Then I can do this U of f operation by using the Toffoli gates in the following way. We have the wires over here, and this is and then we have this auxiliary, right? And what I would do is that I will take this 1, 0, and 1 and apply the controls which are corresponding. So this is will be and then this will be sort of a control NOT gate, right? And then we have the wires like this, right? So what happens when the input 101 is given, then you have uh, this wire, which is the auxiliary wire, has 0. This has input 0 minus 1 over square root of 2. So when you have u of f, this is our u of f for this particular input. Then if I get 1, 0, 1 and tensor 0 minus 1 over square root of 2, then the NOT gate gets applied, and then this converts into get 0 minus 1 over square root of 2 to get 1 minus 0. So there is a minus 1 phase factor which gets kicked back to the top qubit. So this gets to be minus 1, 0, 1 tensor 0 minus 1 over square root of 2, right? So the phase kickback which we learned earlier, um, it's the same thing that gets activated and you get a minus sign in front. So that's the U of F gate. And if you want, let's say there are multiple inputs, suppose you have 0, 0, 1, also another marked element, then you just, after this, you have one more Toffoli, and then you will have, so this will take care of, and you can check that out. You can, this will take care of multiple marked inputs. So that's the U of F gate. Now, what about R of psi? So recall that R psi was a reflection about the vector psi, which is the uniform superposition. So this is where psi is summation over x. Notice that Hadamard tensor n applied on 0 is equal to psi. And therefore, I can write R of psi is equal to Hadamard tensor n to minus identity. Okay, so what we'll do is implement this R of psi as Hadamard tensor n, then this Okay. But how do we implement this? And that's pretty straightforward. Instead of this gate, we'll just implement right? Because of the global phase doesn't matter, right? So how do we implement this? Well, the way to implement this circuit would be just again implement. So this will be controlled by 0, and then and what happens over here if the input is 0, right? So what does this do? If the input is 0, then it goes to, so instead of this, I will talk about this. So input is 0, it goes to -0, and any other input goes to itself, right? So 1 minus 2 k goes to k, right? So you can check that if the 0 input is there, then again due to the same phase kickback, you will get a, so this R psi of 0 will go to -0, right? Because of the phase kickback again. And then on any other vector, the NOT gate doesn't get activated. So therefore, we get the implementation of this. And then we add the Hadamard gates on the side. So this is again, this is 0 minus 1 over square root of, right? So this is how we implement the details of the each Grover iteration. Now it turns out that at this moment, actually, it's a good idea to talk about the query complexity versus the gate complexity, right? So the query complexity in a quantum computing circuit is the number of queries to this black box or oracle, or how many queries to the U of f, how many calls to the U of f function, right? But when we are talking about the gate complexity, then we have to talk about how many gates are required for building the circuit. So for the Grover search, the query complexity is order of square root of n. And one can show that the gate complexity, if I further sort of decompose these type of circuits into single and 2-qubit gates, then the gate complexity is order of square root of n log n. In fact, one can further reduce this complexity to order of square root of n log star n. And this is an extremely slow growing function. So effectively, we have for even very, very large values of n, we can build a Grover circuit with almost square root of n, order square root of n number of gates. Thank you.